Hi everybody, Janet Addison here. I'm the lead for the Grow My SME support that we're delivering in Humber. Just to say welcome, we will have our contact details on the last slide that Mike will give you today, and at some point I'll be following up with an email to see whether you want to engage with the programme in full. But a very welcome to you, and I'll hand over to Mike now.
Hi there, thanks Janet. Thanks Lynn. I've been asked to talk a little bit about our experiences and the work that we do with 3D scanning and 3D printing. And first of all, I've got to apologise that I have a laptop that was built obviously pre-COVID, and it has the camera in the bottom of the laptop. So I'm going to be looking at slides. So I apologise if you're looking at my nose or anything like this, but hopefully you can all see my slides. So this is what I'm planning to talk about: 3D scanning, 3D printing. In terms of who I am, my name's Michael Poole. I'm the Business Development Manager at the University of Lincoln. But specifically, I work for our College of Arts, but it does have a degree of technicality and equipment within it. And specifically, I represent the expertise within our College of Arts. And also we have set up various semi-commercial entities that do work with a range of industries right across the country, and I think that will become obvious with what we do. So in terms of a bit of context, I've told you who I am, who I work for, and I represent both a heritage team that work across the country and a design innovation team that work across the country. Between them and the area of the university that I work in, this is some of the equipment that we use on a fairly regular basis. So obviously 3D scanning and recording and a range of equipment we have there. We do a lot of work with photography, filming, video, audio, music. We do a bit of work, increasingly doing work with VR, AR and mixed reality. And you'll see that we do a lot of work around digital fabrication, digital printing. We do a lot of materials analysis. So whilst we are a College of Arts and we work in the humanities, we have material scientists within our college. We do a lot of work around construction science and obviously 3D modelling. So these are some of the resources that I have access to, and some of our commercial practitioners have access to. In terms of hopefully what you'll pick up from today, I've put together a bunch of learning aims. In terms of data capture, understanding the different types of 3D data capture technologies and the benefits of these scanning technologies, both for the built environment right down to smaller objects and features. And obviously, hopefully, I'll talk about the limitations of some of these processes, because obviously if I'm trying to sell scanners, these companies tend to gloss over these limitations, but certainly I'll try and let you know some of the limitations that we experience. I'm also going to talk about workflow. I think workflow is quite important when we're dealing with a range of new digital design and innovation technologies, from capture to modeling and manipulation through to the various outputs that you can create from that. And some of the processes available to work both within the built environment, historical objects, and products, components and parts. So that's what I'm going to try and cover. I'm going to kick off with the first area of technologies in terms of how we capture and digitize the physical world around us, spatial data capture techniques. I've got this chart here where I think all of you, most of us will know that there's various ways that you can capture and digitize in 3D the world around you. I've put this graph together to try and explain some of those technologies and at the same time some of the limitations that exist with them. So we've got a bunch of scanners here, but equally, in terms of the object size that you're trying to scan, whether it's really sub meters or even sub centimeter, sub centimeter, there's a certain range of technologies that are available to you. But equally, if you're dealing with kilometers, objects over that are kilometers big, there are technologies available to do that. But equally, you get a compromise on accuracy with the object. So the bigger the object, the less accurate it is if you really want super high degrees of accuracy. I've broken it down into three areas: what I would call objects and features, which is and structures, which is where predominantly we work, and landscapes. But with the teams that I work with, we don't do any landscape scanning. Objects and features all the items in red are the technologies that I will talk about. So we deal with structured light scanning that's excellent for sub-millimeter accuracy, as is laser scanning, triangulation laser scanning. We've got photogrammetry as well, which I think will only increase in popularity, ease of use, and spread. And then reflective transformational imaging, which we don't do too much of, but that tends to measure the texture of a surface rather than the geometry of an object. When we come to scanning structures, buildings, or features of building, our favoured technology is terrestrial laser scanning because it's accurate, and photogrammetry and infrared digitization. But there's some interesting technologies here that some companies might want to look out for. And I particularly like the SLAM technology, and I'll try and give an overview of that one as well. But that wasn't going to be the focus of what I'm going to do, but I'll mention that one if I remember. Okay, the first one, when it comes to buildings and structures, we tend to favour terrestrial laser scanning. This is one of the scanners that we use, and essentially it's shoebox sized on top of a tripod. It has a laser on board. It fires a beam onto a mirror that rotates and spins round. So as that rotates, it throws a beam of light out in a 360-degree pattern. And because the machine rotates as well, we throw out a sphere, a laser beam sphere, that when it hits an object, it throws a point back at the camera. So we build up what we call points in space, cloud points. And then this is just I've got a little diagram in the corner in here that it tries to explain how that works. When I do live talks, it's a little bit easier, but essentially it spins this laser around and then it rotates around and it captures a sphere. This slide hopefully will begin to explain what I'm on about. Over here in this point here, hopefully you can see my cursor moving around. That's where the laser was based at this point. And as the laser rotates and throws its beam out, you can see all these points are beginning to be thrown down onto the object and the floor around it. Now, the more the object is perpendicular to the laser, the denser the cloud of points. But as the surface is not as perpendicular to it, you can see the points become more spaced out. The closer to the camera, the denser the points. So ideally, we would take numerous positions of the laser scan here to build up the best possible cloud of points. From here, these clouds of points also have color signals attached to them. And then we triangulate them to create a surface to represent the geometry that exists around us. So the summary for this particular technology is that it is high resolution. It tends to be tripod mounted, although you can attach it to drones, or you can dangle it from scaffolding, or you can lower it into more obscure places, difficult to get to spaces. It tends to be accurate. We can get down to about 3 millimeters accuracy, which is good for a building. You can capture texture and color, although it doesn't like glass. Glass can cause problems, but it will also generate vast data sets. If we scan a building, we will generate gigabytes of data. So if you do go into this field, you need to have good computers to process the data, and you need to have be well managed. You need to manage yourself well. You need to manage your system well in terms of how you manage these vast data files. A lot of the systems we use have got GPS tracking on it, which aids the reconstruction or the meshing of the model into one coherent, into one model of a building. And these machines also work in total darkness because it's throwing out a laser light as well. So we've had 1 or 2 situations where we're working on subterranean crypts. Lighting can be a problem, but with a laser machine, we know that at least we will capture the geometry if we can't capture the color signal. So hopefully that makes sense. Most of our applications for terrestrial laser scanning is in the built environment, and it's in the historical built environment. So this particular project here we've been working on, the red dots represent all the locations of the scanner here. What we're trying to do with this property is to investigate the history of the beams that are in this property. Just as a note here, we've been able to see into the roof structure because there is no plaster and lath on the ceiling at this point. But this is why we've been able to see, get a good image of the interior of the building. What you can see on the outside of the building here is not the outside, it's actually the image of the building on the inside that you can see here. So the terrestrial laser scanner, we can produce lots of nice elevation drawings from it. We can calculate volume and the area of the building, which works for both contemporary construction development as well as the reverse engineering of historical structures. We often use it for things like disaster planning and recovery, or the research as well. It's been used for building asset management or heritage asset management. We can create textured orthographic views from this technology, and it really does help us to reverse engineer and to analyze a structure in a way that some traditional surveying techniques can't do for us. I will be talking about objects and products and components, but I'm sort of talking about the whole range of work that we work on too. We can create doll's house views of an object, these plan views, both traditional vector-based orthographic views and photographic or orthographic views. And this is a detail of a mud and stud building that we were analysing on behalf of the National Trust. And we were looking at its historical significance as well as its structural history. Going back to the one cottage that you saw earlier, we were analysing the timbers on here. We were trying to analyse the shape of them, how they fixed and attached to the property. And we were also analysing the history of these timbers. And this is from a property in Lincolnshire. And we've been able to work out that these timbers grew from a tree just prior to the Norman conquest, and were chopped down not long after to make timbers that were then reappropriated as floorboards in this particular house. So we've not only been able to analyse the structure, but the whole history of these particular timbers, because they have this historical significance. And again, from our scan data, we can go into this, we can add notes, we can measure, so we can take accurate dimensions, etc., because we're dealing with a three-dimensional model. We're not dealing with photographs. We're dealing with a CAD model that we can rotate, explore, navigate, and reverse engineer. These are some examples of some of the cross sections that we take through it to help us analyze the structure using terrestrial laser scanning. And again, we can go into a building and we can create dimensionally accurate orthographic views or elevations or sections of a particular building that we're dissecting to have a look at. Second data capture technology that we use, not too much, but I think we'll be using it more and more, is structure for motion or photogrammetry. This technology, essentially, you use a camera, preferably a good digital SLR camera, to take a series of photographs of an object, either in parallel or in an arc of an object. But a piece of very clever software, we use Agisoft, helps us to recreate a model of an object. So essentially, the software looks at a bunch of photographs and thinks there's something three-dimensional here. It goes through various algorithms to create a three-dimensional model. We like this technology for when we're dealing with remote, difficult to get to places. So this is of a structure from Greenland, some Viking structures from Greenland. And it's much easier to take a camera and a laptop than it is lots of the terrestrial laser scanning gear, lighting, etc., etc. So these are the benefits of this particular technology. But increasingly, smartphones are and iPads, the latest iPad has LiDAR capabilities attached to it. So you will see apps that take advantage of the cameras on smartphones, on iPads and tablets, where you can then put those into an array of software to create three-dimensional objects. But at the moment, the accuracy isn't quite what we're comfortable with some of the work that we get commissioned to do. And again, this is just, I think, my last slide that I've got on structure for motion. But again, this is Viking structure. For us, it's low-cost equipment to capture the data. It allows us to do these rapid surveys quite simply, you can strap cameras to drones so that you can do aerial views, which are again difficult for tripod-based laser scanners. But the processing time is longer, and you also have to take usually the data back somewhere to process that data. So it has its disadvantages as well. This is a quick, rough process outline that my colleague who does the structure for motion has put together in terms of we gather the photos and then we use the software to align them, create the point clouds. And the point clouds, we create a mesh, texture the mesh, we clip, edit the mesh to create a three-dimensional model. That's a very rough summary of the process that we use there. Slides to move on. Okay. This is a third technology that we use. It's infrared laser scanning. It's infrared scanning, and we use this to scan the interiors of buildings. And this is essentially, best way to describe it is Google Street View for insides of buildings. Once we've captured the building, we can very quickly rotate it and move around it. The technology for this says that you can't normally do external spaces, but you can if you're clever. The scanner works using infrared light. If you go outside and the sun is above the horizon, the sun floods the environment with infrared light, and technically you can't scan it. So if we scan an outside space, we go before the sun has crested the horizon. So first thing in the morning, last thing at night. It does mean that we can create what we call a doll's house view. And this will be the subject of my talk on Monday, but very quickly, you can navigate through a building and you can add what we call hotspots. So here we've linked into it a YouTube video that explains the history of poppies and why poppies have played its role in war memorial commemorations, etc., etc. And we use it as well to document things that we've uncovered in this particular structure. So that's a very quick overview, and I've actually got a separate session dedicated to this. Just trying to get these slides to move on. Please. To move on at the moment. Okay. So the infrared technology, again, this is the last slide that I've got on it, but in terms of creating, what it allows us to do is to create a digital copy of a space or place, typically an interior, a venue, a showroom, a gallery, a commercial space, a residential space. We've been using it to for open days. We've been using it to go and scan properties on the Isle of Man, for example, where we add in the research that we find. You can download floor plans from this. You can download 3D CAD models. You can measure from within the object. And it has numerous benefits for the work that we do that relates to the built environment. Now I'm going to touch on the technology that's I'm a lot more comfortable with, which is the structured white light scanning, which we do quite a bit of. It's different to laser scanning. I've got a range of scanners here. These are all the scanners that we currently use. And if you notice, they have a camera on them. So in the case of the two Artec machines, there's a camera in the middle. There's a light source. There's a projector in the middle. There's a light source that typically surrounds the projector. And then there's a series of cameras positioned at different angles. So again, projector, light source, cameras here. Projector, light source, cameras here, and a similar process on this one. The way this technology works is the projector beams a pattern of light onto an object. It beams it on very quickly. In normal circumstances, you won't see that pattern as it does it. But because you've got cameras placed at two different angles, the software behind the machine senses that there's a three-dimensional object there and constructs the geometry accordingly. And then the software then goes on to further refine that. So that enables us to create a three-dimensional object from that we're seeing. In terms of accuracy, we've got machines dedicated to smaller objects here that can get down to 0.05 millimeters accuracy, between 0.05 and 0.1 millimeters accuracy. Whereas the machines in the middle here can get down to 0.5 millimeters accuracy. These two are tethered to a laptop, but this machine here is completely independent It has an onboard computer and it scans much more in real time. It's a little bit heavier, it's quicker, but all of these machines have their horses for courses basically, and we use them for particular applications. In terms of what all these scanners actually produce, what they produce, and I need to emphasize this, what they produce is a polygon mesh. It's a mesh that represents the surface that it sees. It is not the surface itself. It is not the geometry of the surface. On this image here, hopefully you can see it. It's covered in many triangles. The software's optimized the mesh, so around flatter areas, there are fewer triangulations, but around more detail, there are many more triangles in there that forms this mesh that represents the surface. And where a scanner has difficulty seeing, in this case inside the ear here, the mesh, if the camera cannot see the surface, it will not record the surface. As the software's processed itself here, it's interpreted the interior of the ear badly, which we will then have to edit and correct. So the polygon mesh is a representation of the surface that's generated from a cloud of points. We can texture that surface, so we end up with a full color signal for the surface. And then we have to reverse engineer that surface if we want precise geometry. With this kind of object would be very difficult. So my point here is that when we're dealing with industrial components and we scan them, we end up with these meshes that we have to tidy up to convert to precise surfaces. On this object here, you can see that it's not covered in triangulations. What you're looking at here is is precise geometry. It's captured the designer's intent of what the surface is supposed to be, that is completely accurate. And to get from a triangular mesh back to precise geometry is difficult. It's a little bit easier when the surfaces you're dealing with are basic spheres, cylinders or flat surface, etc. But when you're dealing with historical artifacts, it's virtually, you just don't reverse it. You just don't reverse engineer them to precise geometry. There's just no point. I wanted to emphasize that. With any of the scanning techniques that we use, whether we're using terrestrial laser scanners to scan a castle, or using handheld scanners to scan a tablet, or we're using it to scan ceilings or interior aspects of buildings, we really have to think about how we're going to scan an object. You can't just pick it up and wave it around as an object. You can't do that. Even with something as simple as a tablet here, we have to think about what our approach to scanning that will be. We have to assess and plan a space. So certainly when you're dealing with something like a castle, we go for a site visit. What we're interested in is, can we physically get the scanner all the way around the building? Is it best to do it in the winter when there's less shrubbery and natural growth around, or can we do it in the spring or the summer, and can we clear the area to get around there, or will trees and leaves obscure it? So we have to think about the physical access around an object to make sure that we can get around it. And in this case, we needed cherry picker platforms to scan the ceiling. In this particular place, we needed to scan this tablet in an environment that the museum approved of. So you cannot underestimate any assessment and planning. Even if it's for an engineered component, we need to know that we can access the part, that we can handle it, we're allowed to touch it, we're allowed to roll it over, and the room that we're going to scan it in, is it reasonably well lit or not? Sometimes we have to set up and calibrate the scanners, the device, the software for the objects that we're doing, particularly the smaller objects actually. And then we also think about how we're going to process that data, what we're trying to end up with in terms of the fact that we want to create a digital asset. So what kind of digital asset are we aiming to create? Are we aiming to create just a record for something, or are we aiming to create something that will go on to the creation of a physical model or a virtual model? So how we process the data depends on the end result that we're trying to achieve and how we share that information. So I'm hoping that makes some sense. The benefits and opportunities for a lot of these processes, hopefully more of these will become obvious. But Some of the benefits and opportunities is that it's minimal contact. I won't use the phrase non-contact. I know a lot of scanning companies will say that, look, our process is non-contact. That's not true. Virtually with most of the processes, particularly with industrial components, heritage components, there is a degree of contact needed to move the part around to access every possible face of that object. And that might have consequences. We've worked with engineering components where we can't get fingerprints on them too much, or we've had to lay down a powder onto the component. We don't want to disturb that powder. Benefits and opportunities means that we can create an accurate digital record of something. And again, we're doing that for both industrial components. We're working with a company that have to service Land Rovers for the Ministry of Defence. And obviously they're not made anymore, so we have to catalogue a lot of the components. So we're creating a record of industrial components as well as heritage components or objects of cultural importance. We use it to do digital repairs and restoration, which sometimes are a lot easier to do than manual repairs and restoration. Again, I think that will become obvious with some of the examples that I've got. Yes, we're using it for things like heritage interpretation. We're using it for industrial or engineering interpretation and analysis, and it allows us to do remote communication of objects or components. Obviously, for the large components, we do it for things like monitoring, measuring movement analysis, wear and tear on objects. So as tooling is used to run off thousands or even millions of a component, these techniques are used to measure wear and tear on tooling. But equally, we've been asked to measure wear and tear on historical stone steps over a 12-month period. And we can measure how and where these steps wear the most. These techniques are being used to collect 3D evidence. The police use it, the fire services use it, rescue services use it, and other industries use it to capture 3D evidence. And we also get asked to do a degree of reverse engineering. So in an industrial context, it's usually to take it back to precise geometry. In some of the in the built environment context, it's usually to deconstruct the building, to reconstruct the building, or to analyze some of the major structural components rather than every feature of a building. So those are some of the applications that we've got. But equally, I'm going to give you a few case studies that come from both the heritage environment and the industrial engineering world as well. So hopefully you'll get a flavour of what we do and the benefits of the process. This is a property in Buxton, the Buxton Crescent Hotel, that's recently been on the news. It's had a major renovation back into a hotel and spa, and we were there as part of a conservation project to look at surface decoration initially. But we walked past this room where it had got a ceiling that was falling down, and it was a highly decorated ceiling of some very early embossed wallpaper. And we asked them what they were going to do with it, and they said they were trying to repair it, but were struggling to find somebody that could repair it that was historically authentic. And we said, well, can we look at that and propose a method for you? Having no idea as to how we would do this. So we went back and we worked on a method where essentially what we decided to do was to scan it using both handheld scanners and terrestrial laser scanners to scan the whole room. We needed to scan the whole ceiling, and we needed to scan parts of the ceiling. And from this, we were able to reconstruct a three-dimensional part of the ceiling. Now, actually, it's a recurring pattern. This isn't wallpaper, these are paper tiles. And because I can work both with technologists that understand 3D scanning and digital fabrication, and I can work with conservators who are able to take these paper tiles, analyze the paper formulation, analyze the pigments, and they were able to identify that this is a very early form of Analypta. It came out of a factory in the Northwest. This is the paper composition, and this is the exact pigment that was used. So our method statement was that we could digitally recreate these tiles and that we could mold new tiles using a paper formulation that simulated this early Anaglypta wallpaper. And I think that this catalogues what we did here. So this is the new digital tile. And what we've done here is the scanner, from the scan data, what we've reversed engineered is that we've flattened the tile because the ceiling has got a curve on it. We've flattened it. We've been able to eliminate all the paint crazing from it because it had got so many layers of paint on it. We're able to peel all those layers back and create a smooth surface digitally, which was tricky, flatten it. But now we've got a three-dimensional digital model of here, which we've measured, we know is accurate to 1 or 2 millimeters. We then CNC tooling, male tooling and female tooling, that we use to press paper tiles. We proposed this method to them, they accepted it, we produced a sample for them, they signed off, and then we reinstated that ceiling for them. This is the tile that we took a photograph of, that we took along to the architect, the conservation officer, English Heritage, the property development team and the owner, and this is the tile that they signed off. And this is the ceiling that's been reinstated after we've gone in and put these tiles in and repainted them. We've also got the contract to do the friezes around the side here. So why is a university involved with this? Well, for us, this is where we've gone in and effectively we've rebuilt a process to produce not just a paper tile, but a paper tile that is historically authentic. And this has been a great project where there's a lot of buzz within the conservation community as to how you can use techniques to create something that is very authentic in many regards. I must point out as well, I love the fact that this ceiling raise in the middle here, and one of the reasons the ceiling was collapsing is it's actually cast iron. It weighs a ton. And I was quite shocked when they said it was cast iron. So I've gone and touched on a whole bunch of processes that we can scan products and that we can use a range of CNC machinery to help us recreate things, but equally we use 3D printing to help us create things. And I've got a few slides here on 3D printing, but I must emphasize that a lot of people have described 3D printing as being a revolutionary process. And I want to put that into context as to why 3D printing is quite a profound change in the way we manufacture or produce material artifacts or products or components. And essentially, I'm going to give a very quick overview of the history of manufacture in terms of that 1,000 years ago, 12,000 years ago, that the history of manufacture has essentially revolved around two processes, of a subtractive process and a forming process. That here we take bone in this case and we carve off, we subtract something to create an object that means something to somebody. Or we then take a series of minerals, etc., and we cast them into a pattern to create the world's first iron bridge down in Coalbrookdale. Or we take a plaster tool and we pour in a ceramic slip to form something. And as manufacturing has progressed and we go into things like injection molding, we take a very precise tooling steel and we squeeze into it a liquid polymer to injection mold new phone cases, etc., etc. But in the early 70s, various processes were patented, where in 1986, the world's first rapid prototyping machine produced. And we introduced a new way of manufacture, and it was additive, where we take computer code, a three-dimensional model, we slice that code into layers, and then a machine builds layer by layer an object. It's not subtracted anything, it's not formed anything as such. It's taken computer data, a bit like DNA data that Mother Nature uses to grow an object. We've taken a computer data, a computer model to grow an object, an additive process. That's fundamentally the difference. And the consequences of that for designers and engineers is that we get this freedom to manufacture complex structures without the need of tooling. So for example, from the arts, from the creative industries end of things, we've got somebody here who's created a simple fruit bowl. But if we're to use that using traditional subtractive or forming processes, you would need tooling to do this, and probably several stages of the process to create this. not with 3D printing, not with an additive manufacturing process. It's produced in one process, as is the stool, or as you can take this complex air inlet manifold here that's normally made up of a whole bunch of parts. Additive manufacturing, 3D printing can produce it in one hit. So we can consolidate the number of parts. We can simplify the complexity of parts by making complex parts. And we can radically revisit our supply chain and reinvent the supply chain for producing things. We can reinvent the manufacturing process to do things. So some industries are bringing certain processes back from the Far East back to the UK to make certain objects. And we've used it to help create prototypes to communicate a product concept in 3 dimensions to a client much earlier on in the design process. It's been used to create 3-dimensional models where you can take it to an investor to say, this is what I'm thinking of. And because they can see a prototype, a realistic prototype, much sooner, it's easier sometimes to lever in the investment earlier on in the design process. So these are all the benefits of 3D printing, and this is why it's potentially and will become a challenge to the way we make and manufacture physical products and components, physical prototypes, right through to 3D printing finished products and components. I've got an example of a few items here. So table joints here. There's no machining of the actual wooden components here. It's a component that allows to take very simple legs to put together quite quickly. So I like that one because you've not had to, you've reduced the machining operations on other elements because of 3D printing. I like the fact that 3D printing can actually challenge how we weave cloth, where we take a strand of cloth and we weave it into this complex. Well, 3D printing has challenged that. It's actually going back to the days of when we looked at original chainmail to create this very complex system of triangulations that are all hinged together that have produced this garment. And 3D printing has been able to produce this garment in one hit. It's not been assembled. The model was made and it was all scrunched up so that they could fit it within the machine. It's printed, it's taken out of the machine, it's shaken, and you end up with a garment that was, its manufacturing process was file print. I'm being quite crude and simplistic, but that's the potential of this technology. 3D printed parts are being used in anger on finished products. So certainly high value manufacturing industries, aerospace, the military, Formula One, high-end production cars, Bentley, Rolls-Royce, for example, even high-end mountain bikes. On here, you've got a component here that's 3D printed in, I think it's titanium that this one was printed in. So it's being used in a range of finished products today. The dental industry, the jewelry industry, prosthetics, it's being used for to create certain items. And then artists, jewelers, sculptors are beginning to pick this up, and this is just a piece that I quite like, where he's using 3D printing, 3D scanning to reinterpret some sort of really classical Wedgwood items. I quite like that. You can 3D print food. You can 3D print biological materials. You can 3D print electrical components. Not all of them, can't do batteries yet, but it's getting that way. So the range of materials that you can put into a 3D printer is increasing. From both static, biological, electronical, chemical, etc., to produce a whole range of stuff. You can 3D print buildings. NASA are looking to that when they go back to the moon in 2024, one of the technologies that they're seriously considering is that you'll be able to 3D print structures on the lunar surface. But already, construction companies are now 3D printing houses. That is going on now today as we speak. What else have I got here? I'm going to take that back now to some of the applications that we use when it comes to 3D printing, and again, in the heritage industry, as well as products engineering, etc. So this is Kelmarsh Hall down south, where we were again brought in to look at the decorative schemes. They wanted to understand the history of the decorative schemes which is a particular forte that we're good at. And again, normally what happens, we go in there, we ask them questions about lots of other features, and they basically said that some finials above the doorway here were missing. These didn't exist. They got one in storage, and we said, well, we can remake them for you. We can scan them in, 3D print them, make them look like plaster. They'll be above the door and nobody will know the difference. We said it jokingly, but they said, okay, do that. So this is what we did. We scanned an original in, we 3D printed it out, in this case 2 sections because it was quite tall. It was getting on for about 1.5 feet tall. And because we have a team of conservators, I think we're quite good at making things look like a stone surface or a marble surface. It's one of our specialisms. This was one for somebody dug up, being in Lincoln, somebody dug up in their garden a 1st century Roman bull, as you do. It was about 14, 16 inches long. And they asked us, we were commissioned by a design agency to reinterpret this bull so that people with impaired vision could feel the shape of this bull and what it used to look like. So we worked with a professor of Roman antiquities, not from Lincoln, actually from Solent University, Southampton University, to understand what this figure might have looked like. And this particular pose, it's a very classical pose that you not only see in Roman statues, you see it in coins, you see it in reliefs. It's a very, very common pose that they use. And this is what it would have looked like. You can see on the original here that there was a little rest point to support the bull. And we used a combination of traditional sculptors scanning, 3D printing to produce a piece for a museum that they put on display for people with impaired vision to actually go up and touch and feel, so that they could actually engage with history. And I quite like this one because we're using a combination of techniques, including 3D printing, to help reinterpret the past and engage a new audience, which other processes would have struggled to do in the way that we did it at the time. We work with companies to help them produce the CAD drawings of new components. This is one for the construction industry. And we very quickly, working with one of my colleagues, Kev, can produce components. We can show them on the screen, and we 3D print it, and they've gone on to launch a company. It's a safety product for the scaffolding industry, and I know that it's a very simple product, but he's won numerous awards for it because of its safety implications in the scaffolding construction industry. And the beauty about it was that we were able to 3D print and produce an idea of his product much earlier on in the design process. And by having a 3D part, we were able to bring in a tool maker to understand how we could actually cost effectively produce tooling, which meant that we tweaked the design for him, etc., etc. And then he commissioned the tooling and then started to produce the product from there. So that's how 3D printing played a role in help to validate, test, and prove an idea earlier on in the design process. I'm emphasizing this one. This is where we were asked if we could fix a terracotta warrior. Well, three of them. 3 of the bodies of these warriors are cracked and broken, which we fixed and put back together, but there was a head missing. And what I quite like about this project is that the head that was missing, we were able to scan in the 2 original heads, manipulate the data to produce a 3rd unique head, because on the actual terracotta warriors, no 2 heads are the same. So we produced a new head, so it's got a different kind of moustache, it's got a different kind of headdress, a different kind of chin that's going on here, and slightly different formation around the eyes, eyebrows, etc. We 3D print that, and I've put this one as an example because whether it's heritage industry or working with engineers or people producing products, one of the downsides for 3D printing is the finishing. You quite often have to finish a component if you're trying to do something with it. In this case, we were trying to make that 3D print look and feel like terracotta. So we do a few paint trials, etc., etc. We do a few tests on some miniature 3D prints, and in the end, we produced a replica head to the point that we wanted to be able to put it into an exhibition, and nobody could tell that that was 3D printed, and that was the aim of it. So we fixed the various items for exhibition. We fixed the head, and then this went on tour, and we traditionally would play down the fact that one of these is 3D printed, apart from an exhibition that we did, which was all about 3D printing, where we then told the story as to how one of these heads was 3D printed. I want to just summarize some of the things that I'm saying now in terms of the process that we've gone through. I've broken down into 4 stages. We've got this first stage here about capture, that there are various technologies out there for you to capture and record the physical world, the built environment, interiors, full built structures, architectural features, products, components, artifacts, down to really tiny featured teeth or bone structures during operations. There are various technologies where we can capture in 3 dimensions the world around us, from simple photographic technologies through to high-end laser-based scanners that produce very high-quality, accurate models. The second area is the computer, the software that you use to model that data into the third item, a digital asset. And then once you've got a digital asset, you've then got various choices to output that information. Typically, it's either a virtual output or a physical output. I'm emphasizing what seems to be really simplistic, because essentially stage 1 and stage 2 is where the cost is. These will cost you money to do that, but what you're aiming for is to create a digital asset. This stage, the second stage, is where you really add value to what you capture, and it determines what kind of digital asset you create. And I call them digital assets because whether it's a physical or a virtual one, your digital assets have a value. So if you're creating a prototype or you're creating a physical product, it's got a value. The physical product you'll go on to sell, you will generate income from it. The prototype will lead to potentially income and investment. It has a value. But we sometimes estimate the fact that these digital models, these 3D things that we create, have a value too. So for example, some of the artifacts that we scan, and if we create a nice artifact, we can put those out on the public domain with a price to it. So if you wanted to download those STL files, you pay for them. In the same way a photographer takes a picture of a landscape, they charge if you want to use that picture. The same's happening with 3D digital assets. So don't lose sight of the fact that potentially within your industry, as a lot of these technologies are disruptive, you've got the chance to monetize these digital assets, and whether be they physical or virtual. And it's this stage, this second stage, this data processing, that if you guess it right, you lay the foundations to create a valuable digital asset. And also you have to manage those digital assets in terms of how you store them and what you do with them. So I just wanted to emphasize that. I think we're not just playing with a bunch of tools here, we're creating digital assets. To that extent, a lot of the technologies and tools we use, they're great: 3D printing, digital fabrication, CNC rigs. We can scan our world, we can digitally manipulate it, model it, we can create these digital assets. But a lot of these tools that we've got are tools. And it's really important that these new technologies are tools to help us innovate. And for me, from a background in industrial design, it's really important that design's influence on a product cost is huge. And I've got some statistics here, some research that we did where design's influence on product cost is as much as 70 to 80%. Whilst we might think that a finished product's cost is down to its materials, it's down to its labor, etc., etc. If you've got the design wrong, it's expensive. So design influences is cost, or rather design is the seed of cost, whether it's for a physical product, a new service, etc., etc. You've got to get your design right. And to that extent, I'm not going to dwell on this one too much. I want to look at these for me, again, as a designer, having worked in product development, what I'm trying to say here is that if I took a very simple design process where we might be presented with a problem, which we will need to understand that problem. We need to turn that problem upside down. We need to look at it. We need to analyze it to understand that problem. And when we really understand that problem well, we as designers, engineers, etc., we define that problem. We say, what is the thing that's really causing us? What is the problem that we need to solve? We then go through a concept phase where we produce a number of solutions that we test, we verify before we sign that off. And then we shift from these 3 stages here, which is all about problem definition, coming up with new concept solutions, into an implementation phase where, okay, now we want to do something with our new solution. We want to detail it up, prepare it for production and launch it. A lot of these technologies, these 3D print technologies, these scanning technologies, etc., are great to help this front end of the design process. A lot of the companies that I've worked with in the past tend to start designing too late. They tend to start designing at this stage because they want to get here. And it's usually because they don't understand what we often refer to as the fuzzy front end. That, well, how do you define a problem? How do you go and talk to consumers to find out what they really want? Because we're trying to shorten, we're trying to be clever at this stage. And the best way I can sum it up is that what 3D print technology is doing, by being able to create a prototype or capture our world in 3 dimensionals earlier on in the design process, it means that if we need to change our mind, if a client says, actually, I don't want it that big, I want to do something differently with it, we need to know about it at this stage before we invest in exponentially more expensive processes later on, like tooling, like marketing campaigns, like websites, etc. This is where you need to change your mind here to get the product right. We want sign off at this stage. We don't want sign off later down where it gets so much more expensive. So this is where you do your design and development here. You cannot start your design and development later on. And it's these technologies, it's these new design to development technologies, the scanning, computer modeling, 3D printing, that allows us to try and get this feedback from clients much earlier on in the design process. So this slide I've put in here, I'm working with one company, Fisco, south of Lincoln, where initially they came to us and they said, we design Christmas decorations, a really, really simple product. They design Christmas decorations, and they basically said, can you help us come up with some fancy new Christmas decorations? And this is why I say problem definition is really, really important, because we're chatting to them about saying, okay, yeah, we can help you design some new Christmas decorations. But as we're talking to them, they're saying that, well, look, we're actually only profitable for 3 months in the year. The rest of the time, we're not profitable. I'm saying, well, isn't that the problem you want us to solve? How can we make you more profitable during a greater part of the year rather than just 3 months of the year? Why can't we work with you to solve that problem? Because for me, that's an interesting design problem, an interesting business design problem. So it's no longer we're designing widgets, we're actually reinventing the company to some extent. And the solution was that we wanted to look at festival decorations. We wanted to look at, and that was one part of it. What are all the other festivals that we can help you with? And the other one as well was that you're designing products for an end user, but why don't you design a service as well? Why don't you design a service where you can go into shopping malls, you can go into people that rig out ocean liners, you can, where you take on a contract for them, where you design their whole scheme, you go in, you fit it, you install it. So that it's a new strand to your business. And this is how the business, the problem was redefined here to help that business do something strategically new, rather than come up with new Christmas decorations. So I think understanding your problem and doing your research can reinvent your business. So I think I've got one more slide after this. I'm about done. In terms of some of the limitations of scanning, some of the pitfalls, in terms of scanning, it's not a non-contact process. If you want to work with scanners, if you think my business would really benefit from a scanner, don't be hoodwinked by the companies out there that say it's a non-contact process. It is a contact process. You have to handle the object to scan it. that you are only producing surfaces. You're not delving into the depths of the scanner will only scan what it sees. And again, it's a polygon mesh. It's a representation of the surface. It's not the fine geometry. I've got this conversation I'm having with a company at the moment. Exactly what are you looking for? Are you looking for precise geometry or a representation? It's line of sight. The scanner will only record what it sees. Access can be difficult, even if it's an object. Well, the object's up in Glasgow. Right, okay, so there's travel expenses to go to Glasgow. And it's in an environmentally controlled room, right? Okay, can we have access and authority to go in there? Health and safety, working at height. We need to get close to that ceiling. We need a cherry picker to be able to go and scan those tiles, or an architectural feature. Data and digital assets. Reverse engineering can be very complex. It's very easy to take precise geometry and convert that into a mesh that you want to put into a 3D printer. If you've got a mesh that you want to create into precise geometry, really difficult, very time consuming, particularly if the geometry is complex. Creating watertight models. A few years ago, this was a problem. Increasingly, it's getting better. That when you have a polygon mesh, sometimes there's a little hole in it or something, and the geometry hasn't probably worked out. It can be a pain. A 3D printer, a CNC rig wants watertight geometry. And then managing your data assets. We're generating huge file sets. We need to be able to back them up. Initially, we were sticking them all onto hard drives or computers. That's not acceptable. This isn't. You're not just storing a file. You're storing a digital asset. It has a value. Replication, reproductions and replicas. The more you scan something, the more you gradually lose some detail. So accuracy can be important. So how important is the accuracy to your end client? And finishing, unfortunately, finishing can be really labor intensive still. And so there's a big cost there sometimes for some of the stuff that we work on. So all these are 3D scans that you can see here, that they're not images, that they're difficult for us to finish off sometimes, as we have with this statue down here. I've got a feeling that actually rotates. Yes, it does. And then the last one, process and skill sets. If you are an analog business and you want to become a digital business, you want to become a digital business working with 3D digital technologies, you might have to reinvent yourself. You'll obviously have costs to look at. Scanners can be expensive, but they'll get cheaper. The software to run these scanners are expensive, but they are getting cheaper. 3D printing's obviously got a lot cheaper, but the budget end of machines are still quite crude. So there could be an expense in the hardware and the software, but then reskilling people can be expensive. But also strategically, you can reinvent the processes to do something. So for example, the ceiling that we did, the property development company went to a traditional wallpaper tile manufacturer to get these tiles made. They quoted 6 figures to do that. With the process that we put forward, we didn't. We were tens of thousands to reinvent, to provide a new process to produce an historically authentic tile. We offered them a completely new process. And within that industry, we've been asked to go and present papers and talk about how we did it. So yes, there can be these costs in setting yourselves up with these processes, but also it's an opportunity to reinvent and to become more productive with what you do, and to provide completely new outlets for what you do, because you've got these digital assets that you can work with. Okay, yeah, the summary of what I've got. Hopefully I've described some of the 3D capture technologies that we've got, the laser scanning, structure for motion, white light, etc., etc. I've given you an idea of the workflows that we go through and the benefits and limitations that has, and the potential outputs that you can create. And I've shown that hopefully through a range of samples that we've got here. And I think that's pretty much it. I've got this one slide here that says who I am. I've got my phone number on there and my email address. And that just gives you an overview of our experience of digital fabrication technologies, scanning, etc., etc. So Lynn, Janet, I'm done. And hopefully that was reasonably.
Thank you very much, Mike, for that. That's really interesting. Does anybody have any questions for Mike, if they'd like to unmute themselves and put a question in?
I'm looking at 3D printing from an architectural point of view, more than the scanning aspect of it. And obviously, like you say, there's hundreds of different versions of different 3D printers that you can buy.
Yeah.
Is there a good sort of budget for a small scale printing that I would use?
I think out of the budget machines, the ones that we tend to have leaned to, if you're making bigger models in an architectural situation, the two technologies that have really taken off for architects is laser cutting.
Yeah.
And when it comes to 3D printing, two machines that I like are the Ultimaker machine and Formlabs. Formlabs will cost you probably about $2 or $3 grand, and they're good for models that are about the size of a grapefruit. If you're producing an architectural model, you might use traditional card and flat sheet material to create basic layouts and to create some contours, but on there you could put quite a high quality Formlabs based model. And because I work with the School of Architecture and the built environment, when they make models, they tend to use laser cutting and 3D printing, and the machines they use have been the Ultimaker, MakerBot, and Formlabs. Right. Personally, 3D printing, it would be Ultimaker and Formlabs. MakerBot I'm not such a fan of, but the machine that architects tend to love within our school, the students love, and the architectural practitioners we work with, they love laser cutters.
Right.
Because you guys create lots of two-dimensional vector drawings, and from there you can stick it over to a laser cutter, and you can cut out all these profiles and create all it's flat surfaces. A lot of it is flat surfaces, and it's great for that. And you can contour it up too. Laser cutters has been really popular.
Right. Okay. Thank you.
Any other questions? No, I think not. Okay. Thank you for your time, Mike. What we'll do following this is we'll get in touch with each of the participants individually and give them the contact details for the Humber programs of support that's out there, and hopefully you'll be able to engage with us, and we can support you on your journey in any of these techs or even smaller scale techs.
Sorry, Janet, to interrupt. And just while you're speaking, I'm going to launch the satisfaction poll for the webinar as well. So if you wouldn't mind just filling that out before you leave as well.
Okay. The other thing as well is if any of the companies are operating in the greater Lincolnshire area and you're a small, medium-sized enterprise, the university has access as well at the moment to some business support grants, productivity vouchers that will buy you about 20 hours of university expertise to help solve a problem, to come up with something innovative. And I'm more than happy to talk to companies about that. And any other grants that we sometimes have access to, but that is the immediate one that we have access to. But that is for Greater Lincolnshire, North Lincolnshire, North East Lincolnshire, and Lincolnshire.
Thanks for that, Mike. So yeah, please fill in our feedback poll, because we have to do that to secure our funding. So we welcome just 3 minutes of your time to do that. Yes, thank you very much for your time, and we'll be in touch to follow up with you.